Let's understand the RMS prop optimization algorithm. Imagine this landscape as the loss contour, where the center represents the minimum we want to reach. Below it is the gradient descent update equation, where theta represents a parameter or a full matrix of parameters in our model. Now, plane gradient descent can become quite unstable during optimization. It takes huge aggressive steps in steep directions, often overshooting the bottom, while taking tiny, cautious steps in shallow directions where we actually need speed. Because of this imbalance, the path toward the minimum becomes zigzaggy, slow, and inefficient, wasting both time and computation. Now, imagine the vertical direction here represents the weight parameter W and the horizontal direction represents the bias B. What's happening is that our optimization path is taking huge steps along the weight direction, but relatively tiny step along the bias direction. This imbalance is a problem because ideally the movement should be more controlled vertically and more effective horizontally. So the algorithm travels smoothly towards the minimum. But plane gradient descent does not know this. It just uses one global learning rate for everything, causing instability in one dimension and slow progress in the other. So what we really need is a way to ensure that each parameter can have its own effective learning rate. That way, the optimizer can take the right sized step for every parameter. Smaller step when the gradient is steep and larger step when the terrain is gentle. Now let's introduce the term GT to represent the gradient. We are doing this just to make our visuals cleaner and easier to follow. Now, to achieve this adaptive behavior, we use something called an exponentially weighted average. If you are not familiar with this concept, I have already made a 6-minute animated video explaining it in detail. I highly recommend watching that first because once you understood exponential averaging, this entire RMS prop algorithm becomes instantly intuitive. Now, this value Vt here represents the average at time step t, and we calculate it using a hyperparameter beta. The formula is basically beta times the previous average plus 1 minus beta times the square of the current gradient. We square it because we don't care if the gradient is positive or negative, we only care about its magnitude or how steep it is. For a single parameter, this is just a simple squared value. But if it is a vector or matrix, then the squaring happens element wise, meaning every individual entry is squared separately. This hyperparameter beta is a value between 0 and 1. It controls how much of the past gradients we want to consider. A higher beta means we are including more history, and the lower beta means we are focusing more on recent values. This is the same idea we discussed in detail in the video on exponential averages. Now the idea is to scale the gradient update by the inverse of the square root of this value, Vt. And that's exactly where the name root mean square comes from, because we are using the root of a mean squared quantity to control our step size. Now, if you look closely, the effective learning rate, meaning alpha scaled by 1 upon under root Vt, now depends entirely on the magnitude of the squared gradient. In actual implementation, a small positive value called epsilon is added to the denominator. This is done to avoid any division by zero issues and to keep the update numerically stable. Epsilon is extremely small, something like 0.000001, just enough to prevent the math from breaking if our average ever hits 0. Now, when we use this updated equation, the optimization becomes much more stable and the model starts moving smoothly towards the minimum instead of wild oscillations and uneven steps. RMS prop adapts the updates in every direction, leading to a far more controlled convergence. Now, to build intuition, remember the weight and bias parameters? In the weight direction, the gradient is very large. That means its square is also large, which produces a large value of Vt. And since Vt is large, the denominator becomes large too. A large denominator means the effective learning rate becomes very small. So the update in that direction becomes small and stable. This is exactly what reduces the oscillation we saw earlier. Now look at the bias B direction. Here the gradient is small, so the squared gradient is also very small. This makes Vt smaller, often smaller than 1. A small denominator makes the effective learning rate larger, allowing the update in the bias direction to be bigger. So RMSProp naturally shrinks the update where the gradient is huge and amplifies the update where the gradient is small, balancing the movement in every direction. So that's it for this video.